Whenever you just switch on, instantaneously the bulb glows, the electric pulse travels. You know, electric pulse travels with 1/10 of speed of light. But if you talk about the drift velocity of the electrons inside a conductor, that is 10 to minus 4 meter per second, roughly 3.6 10 to minus 4 kilometer per hour. Just see, if you convert it into in meter per hour, the 0.36 meter per hour it will travel, or in inches 14.17 inches per hour, means roughly 1 feet plus 2 inch in an hour. But when you switch it on, it travels with a 1/10 of speed of light. How amazing concept it is. The concept is basically the drift velocity Vd equal to I upon NAE. This is the formula. N, number density, A, area of cross section of the conductor, E, the charge on electron, 1.6 10 to minus 19 coulomb, I is the current in ampere, and another formula is Vd equal to EE tau by m. E is electric field, tau is the relaxation time, the time between the two collisions, and m is the mass of electron, Vd is the drift velocity. Now the question is, why it is so quick, despite it is of just 1 feet plus per hour? I'm going to tell you, interesting. You know, there are 10 raised to power 28 electrons per meter cube in metal, say copper, on an average. Now, in the metal, there are 10 to raise power 28 free electrons. They are moving randomly. But when we apply an electric field by means of a battery, so they keep on colliding with each other, but they get a direction. Electron starts drifting negative to positive. The 10 raised to power 28 free electrons are so crowded, the pulse is given to 1.14 meter, or you can say 1 feet few inches, you know, like this in an hour. But that pulse accumulates, 10 raised to power 28 pulses accumulates, and it is 1/10 of speed of light, 1/10 of c speed of light. That is 3 into 10 to raise power 9 upon 10, 3 into 10 to raise power 8 meter per second. So the electric current is so quick, but in fact it is traveling, electrons are moving just 1 feet or 2 inch in an hour. Thank you.